No, yeah.
Because I technically do math in my head.
Oh yeah, it's just like
All right, y'all, so we're going to pick up where we left off last time with these Grignard reactions. All right, so everybody take a second and try to predict the product of this Grignard reaction here, right? That MgBr organometallic compound is our Grignard reagent. I also want you to take a second and label what is your nucleophile and what is your electrophile in this reaction here. These are things that we want to keep in mind for each reaction. It's going to really help us better understand why the reaction is occurring, and we're going to see patterns over and over again throughout the semester. So yeah, keeping these in mind is going to be very helpful. All right, so which one's our nucleophile, the Grignard or the aldehyde, or the ketone rather? My Grignard is the one with a lot of electron density, specifically at that carbon right there, because it's bound to a metal. Carbon is way more electronegative than a metal magnesium, so it's pulling all that electron density onto itself. All right, our electrophile is going to be that ketone, and specifically which site on our ketone? Electrophilic carbonyl carbon. Is that what you said? Mm-hmm. Yeah, okay. You can hear me say that over and over again. We want that embedded in our brains. Electrophilic carbonyl carbon plays the role of an electrophile all the time. And so this is where my new carbon-carbon bond is going to be. I'm going to redraw my 4 carbons from my electrophile, right? I had 1, 2, 3, 4, 1, 2, 3, 4, and I'm going to mark that formerly carbonyl carbon here. When I draw my new bond, what's going to be on the other side of that new bond is that red carbon, right? My nucleophilic carbon from my Grignard. My Grignard also had these other 3 carbons, or rather a total of 3 carbons. So I'm going to make sure it has a total of 3 carbons. And then there's one more thing that I'm missing, the functional group in this molecule, right? We're in our alcohols chapter. I have an alcohol product. Where should that hydroxyl group go? On that formerly carbonyl carbon. All right, cool. And so in this reaction, as we pointed out before, we have this new carbon-carbon bond between our Grignard nucleophilic carbon and our electrophilic carbonyl carbon. All right. So now we're going to work on going the other way here. What if we're given an alcohol product? All right, and we want to propose how we can synthesize it using a Grignard reaction. So I want you all to give this a shot here. What would be my aldehyde or ketone substrate, and what would be my Grignard reagent that I would use to synthesize this following alcohol? And I'll tell you, there's actually two different ways, perfectly equivalent ways in which we can do it. Just try to come up with one. All right, so let's look here. Like I said, there's two ways, but let's just sort of work through one of them here. Okay. The one thing I know for sure when I look at this product is that this carbon, if I'm going to be using a Grignard reaction, that means this carbon right here must be my carbonyl carbon. All right, it's got the hydroxyl group on there. That's for sure got to be my carbonyl carbon in my reactant. All right, but I could have either one of these be my new carbon-carbon bond. Depending on which one I pick, that will change what aldehyde, in this case, yes, aldehyde and Grignard that I'm going to use. So in my first example, I'm going to choose this one on the left. Right, well that means that these two carbons are in my aldehyde, and the other ones, these three carbons, have to be from my Grignard, right? That new carbon-carbon bond is what joined them together. Not only that, but this carbon on the other side of my new bond must be where the magnesium is in my Grignard reagent. Right? So if that's my new bond, the one on the left of that carbonyl carbon, that means I need to use this 3-carbon Grignard with my magnesium on that third carbon. All right, here's my 3 red with that nucleophilic carbon. Okay. My other 2 carbons were my aldehyde. Right, and in particular, the one that had that OH group on my reactant side has that carbonyl oxygen, is a carbonyl group. All right, I could have also made this same alcohol. Again, looking at this product, I know this has to be my carbonyl carbon, but now I could say, all right, well then this is my new bond. All right, that means on the other side of that new bond is my Grignard. So in this case, that would just be a single carbon Grignard. And my aldehyde would be all 4 of these carbons here. Boom. All right. either one of these approaches could be used to synthesize this alcohol, either having a 2-carbon aldehyde and a 3-carbon Grignard, or having a 1-carbon Grignard and a 4-carbon aldehyde. Either one of these would lead to the same product. All right, and that's the case oftentimes. Not always, but often you can synthesize a particular alcohol using more than one set of reagents. All right, let's do one more. Space those out weird. It's going to bother me. This one also has 2 perfectly logical ways to get to that one product. See if you can't come up with both of them here. All right, so if I'm looking at this here, I know that this carbon right in the middle bound to that hydroxyl group has to be my carbonyl carbon. Okay, there's then these 3 bonds that could potentially be my new carbon-carbon bond here. All right, I'm going to pick this one furthest to the left here between that benzene ring and that carbon. Okay, so if I pick that as my new bond, this would be my ketone, and this would be my Grignard. All right, so in this case, that benzene ring has that magnesium bromide, that's my Grignard, and this 3-carbon ketone. Does anybody know what this one is? It's got a fancy name. Use it all the time to clean glassware. Acetone. All right, so that's our structure for acetone. Okay. If I pick one of the other ones, and you can convince yourself there are these two, however, either one that you would pick as your new bond would give you the equivalent answer. All right, well, if that's my new bond, then on the other side here, I just have this 1-carbon Grignard. And this whole thing, whoops, including that benzene ring, is now my ketone. All right, well, I want to make sure to count carbons, so I got my 6 from my benzene ring, 7, 8. So I need these two here. And importantly, my hydroxyl group would have been on this carbon on my product side. So that's going to get my carbonyl group. All right, and these are one of the reasons why Grignards are so widely studied. We're going to talk about them, kind of revisit them over and over again. And this sort of flexibility is a great example, right? We didn't have any limitations on what we could make our Grignard with. We could put a benzene ring on there or something as small as a methyl group. Anything works here. These reactions are very robust. Do you guys do this in the lab? Do you know? I wouldn't be surprised if you do that at some point this semester. It is just a very good reaction. It works great, sort of good efficiency. And again, it's a great way to synthesize molecules because you're creating new carbon-carbon bonds. All right, cool. So we're going to move on now, talking about another category of reactions. Oxidation reduction reactions. Okay. You first talked about this in general chemistry. You had that really pain in the butt way of finding oxidation numbers. These were these reactions, these redox reactions that you had to balance using that half reaction method where you split it up. It took forever. In organic chemistry, we get to simplify things a little bit because we're talking about such few elements on our periodic table. So we're going to just say oxidation is simply creating more carbon-oxygen bonds. And reduction means that you're creating more carbon-hydrogen bonds. All right, and these processes are inverse of one another. All right, so if I took, for example, an alcohol, I could oxidize that to create an additional carbon-oxygen bond. So now I would have a ketone. And if I took that ketone, I could do the exact opposite. I could reduce it, and that would give me my alcohol. All All right, when we oxidized our alcohol, we created an additional carbon-oxygen bond. When we reduced our ketone, we created an additional carbon-hydrogen bond. Where is that additional carbon-hydrogen bond? Our hydrogens are not explicitly drawn here, so if I'm saying reduction is creating a new carbon-hydrogen bond, where is that new carbon-hydrogen bond?
Carbon and carbon.
Yeah, carbon 2 here. Boop, boop. That's that new bond on the left-hand side that wasn't there on the right-hand side, right? Remember to fill in your implicit hydrogens. All right, cool. So we're going to pick these apart here, talk about them individually. We're going to talk first about oxidation. All right. We're looking at the oxidation of alcohols, okay? But importantly, we're going to need to learn this classification system for alcohols. We have a classification system for carbons. We know what primary carbons are, secondary carbons, tertiary, etc. We got the same classification system for alcohols, or a very similar classification system for alcohols. Now, a hydroxyl group, by definition, can only be bound to one carbon, right? It's necessarily an OH, so that oxygen can only form one other bond. So really we're looking, when we call this a primary alcohol, it's because our hydroxyl group is bound to a primary carbon. All right. This one here, my hydroxyl group is bound to a secondary carbon, so this would be classified as a secondary alcohol. All right, so then just by analogy, everybody take a second and draw me a simple example for a tertiary alcohol. So our tertiary alcohol is when our hydroxyl group is on a tertiary carbon. Okay, cool. So we have this classification system because we're going to see that primary alcohols oxidize different than secondary alcohols, different than tertiary, right? So step one, when we're thinking about oxidation reactions, is to think about the classification of these different alcohols. All right? So let's focus on primary alcohols first. Okay, for right now, I'm going to just leave this as this O in brackets, which is this symbol that we use for oxidation. We'll talk about the actual reagents that we could see doing the oxidizing here in a second. All right, so if I create one additional carbon-oxygen bond here, starting with my primary alcohol, what functional group am I going to have? Just like before, we're going to see this is oxidized from being a carbon-oxygen single bond to a carbon-oxygen double bond. All right, so what would we call it if we replace that with a carbon-oxygen double bond?
Aldehyde.
An aldehyde. So our primary alcohols, they can oxidize to aldehydes. All right, but in an aldehyde, that carbonyl carbon has an additional hydrogen on there. So this can actually undergo one more round of oxidation to create this fully oxidized carboxylic acid group. All right, and you just want to sort of take a step back and convince yourself that at each step here, you have created an additional carbon-oxygen bond on that particular carbon, on that primary carbon. All right, if we were to, everybody take a second and give me the product here for oxidizing this secondary carbon. If we oxidize this secondary carbon, what's our functional group? Ketone. And you will hear me complain about how stupid it is that we classify aldehydes and ketones differently, but regardless, we do have a different name when it's an internal carbonyl. This is a ketone. All right. Now, our ketone carbonyl does not have any additional hydrogens on there. So a ketone cannot be further oxidized. You're stuck at that step there. All right. And then lastly, if we oxidize a tertiary alcohol, right, I take that carbon-oxygen single bond, whoops, and I make it into this carbon-oxygen double bond. Cool, all right, everybody's looking at that like, wow, that looks awful. I hope everybody's organic chemistry brain explodes looking at that because that carbon has way too many bonds, right? So absolutely, this thing does not exist. You cannot oxidize a tertiary alcohol for the same reason that you can't oxidize a ketone. There are no more hydrogens on that carbon to be replaced with oxygens. All right, so tertiary alcohols cannot be oxidized at all. Cool, all right. So I just left this as like O for oxidation here. Let's talk about our oxidation reagents. Okay. We are going to have two buckets for our oxidation reagents, what we're going to call our strong oxidizers and what we call our weak oxidizers. All right, our strong oxidizers, one of which we've seen before in this same context of oxidation reagents, is sodium dichromate. All right, one that's kind of taken, I don't know how to say it, is becoming more popular because chromium, it turns out, is just awful for the environment, so it's really expensive to dispose of in the lab. So labs are trying to get away from using chromium-based reagents. Another popular one is potassium permanganate. Doesn't have the same environmental hazards as the chromium-based ones. Okay, depending on the age of your textbook, you'll see a lot of chromium-based oxidation agents in older textbooks, and you'll see some of these other ones in newer textbooks. Same thing with our weak oxidizers. Our weak oxidizer, the first one is PCC I don't remember exactly what it stands for, except for that one of the C's is for chromium. It is another chromium-based oxidizer. Again, kind of falling out of fashion. And there's a new fancy one, DMP, Desmartin Pyridine, something like that. All right, so we got these two buckets, strong oxidizers and weak oxidizers. All right, so why are we classifying these differently? They both perform oxidation reactions, all right? But if we go up to the top here, if we were to take a primary alcohol and we were to use a strong oxidation agent, we would see that it does not stop at that aldehyde step. It just blows completely past it to fully oxidize this compound to a carboxylic acid. Right? So that's what one of our strong oxidizers will do. They will convert alcohols all the way to carboxylic acids. If instead we wanted to stop at that aldehyde step, that's when we would need to use one of our weak oxidizers. A weak oxidizer will convert a primary alcohol to a aldehyde. All right, for a secondary alcohol, you don't have the same problem. So regardless of whether you used a strong oxidizer or a weak oxidizer, they would both do the same thing. They would both convert a secondary alcohol to a ketone. All right, and then a tertiary alcohol, doesn't matter what you do, you're not going to be able to oxidize it, right? Tertiary alcohols cannot be oxidized at all. All right, so we have our strong oxidizer, which can be used to fully oxidize a primary alcohol to a carboxylic acid. Or we could use a weak oxidizer, which would take our primary alcohol, just that one oxidation step, to an aldehyde. Either one of these could be used to convert a secondary alcohol to a ketone. All right, so let's just do an example that kind of encompasses all these different ones here. All right, we're going to take this molecule. It says a bunch of different, a triol. We got a bunch of different hydroxyl groups in here. And we're going to see what happens first if we treat it with one of those weak oxidizers. And second, if we treat it with one of our strong oxidizers. so this example kind of is going to be used to illustrate the differences between these three here, these three categories, classifications of alcohols, because we got one of each in this molecule here, right? So which one of these would be my primary alcohol, orange, blue, or green? The orange one would be my primary alcohol. What about my secondary alcohol? The blue one. And my tertiary alcohol, my green one. Okay, so a weak oxidizing agent like PCC will turn my primary alcohol, I guess I can be lazy, into an aldehyde. And it will turn my secondary alcohol into a ketone. And it won't do anything to that tertiary alcohol because you can't oxidize tertiary alcohols. All right, so in this case, I'll have an aldehyde and a ketone and my tertiary alcohol in my product. If I were going to do my strong oxidizing agent, that's going to turn this primary alcohol into a carboxylic acid. So I'm going to have to draw in my carbon-oxygen single bond, carbon-oxygen double bond, as well as now another hydroxyl group, making my carboxylic acid. And a strong oxidizing agent will do the same thing as a weak oxidizing agent to that secondary carbon, converting it into a ketone. Right? Even the strong oxidizing agent can't oxidize the tertiary alcohol, so we're stuck. Right? So the big difference here, we're looking at what happens to our primary alcohol. We get an aldehyde with a weak oxidizing agent, and we get a carboxylic acid with a strong oxidizing agent. Both will convert this secondary alcohol to a ketone, and neither will be able to do anything to our tertiary alcohol. That stays the same. All right, so here is our sort of summarizing all of our oxidation reactions here. Cool. All right, and then how do we go the other way? So now let's talk about reducing agents. All right, our reducing agents, we're going to have two of them. Sodium borohydride and lithium aluminum hydride. In each of these, when you use them, you have to do an acidic workup type step afterwards. All right, sodium borohydride, lithium aluminum hydride. They both have that word hydride in there. All right, when you hear hydride, you think a nucleophilic hydrogen. All right, now nucleophiles are what? Electron rich or electron poor? These are the ones that are electron rich. So a nucleophilic hydrogen is weird, right? We never see hydrogen playing the role of a nucleophile. Hydrogens are usually like acids. They're usually very proton poor, or rather electron poor. So in this case here, what's making these compounds unique is they have these nucleophilic hydrogens. They have hydrogens with a lot of electron density that are going to play the role of a nucleophile. And in this case, both of these cases, the metal isn't actually doing anything. It's the hydride, the anion, that's going to be involved in your reaction. So that borohydride, if we want to draw out its Lewis structure, or the aluminum hydride, same idea. 4 hydrogens. And that net negative charge. All right. We're going to do our reaction mechanism here. You can use the full Lewis structure, or we can be kind of lazy. We only really need one of these hydrogens to show explicitly. And so this is the sort of form of our molecule that we'll use in our mechanisms here. All right, this is our active reducing agent, that borohydride, both its Lewis structure and this kind of more condensed form that's going to be a little bit more convenient. Okay, so let's do our reduction reaction mechanism. All right, starting out with an aldehyde or ketone. I'm going to do this ketone here. And our reducing agent. All right, we said that our hydrogen is going to be our nucleophile here, right? That's kind of the weird thing about these hydrides, is that hydrogen's glowing red hot with electron density. It's got a ton of electron density on there. All right, so if we're going to react this with a ketone, what do we think could play the role of the electrophile? Which specifically would be my electrophilic site? The carbonyl carbon, right? Electrophilic carbonyl carbon. You're going to hear me say it over and over and over again. Always playing the role of the electrophile because that oxygen is stealing all that electron density away. All right, so our first step here is going to be this nucleophilic attack. Our nucleophile is going to attack our electrophile. And as we saw before, that's going to kick this pair of electrons onto that oxygen. But there's a problem with how I've drawn it right now. All right, what's wrong with that first arrow? All right, so we can't have the base of our arrow at an atom. It has to be at a pair of electrons. We saw the same thing with our Grignard. In fact, the reaction mechanism between this and a Grignard is basically the exact same. But yes, similarly to before, we have to start at this pair of electrons and end at that atom. All right, so everybody take a second and draw me my intermediate for this reaction. All right, once you get there, I'm going to tell you that the next step is that acidic workup where we add in some weak acid, some source of hydronium, and that's how we're going to get our alcohol product. All right, so once you get those intermediates, fill in the missing electron pushing arrows in order to get to the product side here. So importantly, now I have a new carbon hydrogen bond. I'm going to explicitly draw it in here. That's my nucleophilic hydrogen bound to what was formerly my carbonyl carbon. My carbon-oxygen double bond has been broken, and that pair of electrons is now on that oxygen atom, giving it that net negative charge. Okay? We will see these because the carbonyl carbon plays the role of an electrophile all the freaking time. We have a special name for these intermediates that were formed. We call these tetrahedral intermediates. Because our carbon went from being trigonal planar in our ketone to being a tetrahedral when it got attacked by that nucleophile. Cool. All right, I got one more step to go here. At this point, again, is that acidic workup. I'm just going to protonate that oxygen in order to form my alcohol. I'll draw in my implied hydrogen here, which was that new hydrogen that was added to form my product. Cool. All right, and we will just keep going with our alcohols discussion next class period.